Our lab today will be very interesting and important. However, it won't be that long. I think we will finish maybe like 30 minutes earlier than usual. The lab will be about flow measurement and energy equation. In this lab, we are going to know how we can use the energy equation to measure the flow rate in closed conduits, aka pipes. And to do that, we will use three different measurement devices: the Venturi Tube, the Venturi Tube, and the nozzle meter. The equipment we are going to use today is called the hydrodynamic strainer, this one in front of you. Mainly it consists of a pump and a reservoir. The reservoir that consists water, and the pump will pull the water from the reservoir through the pipes to our system. And of course, we will have some piping manifolds and the pressure measurements devices that we are going to use. If you would like to see a better look at this equipment, I have a picture for it here. Of course, it's just in front of you, but in case if you can't see it clearly, here we have the pipes, and this empty space we are going to insert the measurement device. We have three devices, so at each experiment we are going to attach one of these devices to the system. Great, so why we are interested in measuring flow rate? Because actually it's the most important thing in our applications. You would like to know what is the flow rate that is passing through a certain pipe. And you can do that with two ways. You can do it directly by using a fluid displacement meter, something that looks like this. This is called a displacement meter. Or actually, in most cases, because this is not practical, we use the indirect method. And the indirect method involves the usage of one of these three equipments, or one of these three devices. Before getting into the measurement devices, there is a very important concept that you should be familiar with. When you are dealing with pipe flow or conduit flow, there is a very important assumption here that the velocity at the conduit wall is equal to 0. So what does that mean? Just imagine that we have a certain conduit, a pipe. This is the boundary of the pipe. The red line represents the wall of this pipe. And we have water flowing from this direction. And this is simply a chart for the velocity distribution across the conduit cross-section. The x-axis shows the velocity, and the y-axis shows the distance from the wall. So exactly at the wall, you will see that the blue line and the black line is at 0. This means that the velocity of the water at the boundary or at the walls of the pipe is equal to 0, and it starts to increase by going further from the pipe wall until it reaches the maximum value, the maximum velocity, just at the center line of this pipe. So what's the difference between the two lines, the blue line and the black line? The blue line is the water distribution or the velocity distribution in case of turbulent flow. We have two types of flow. We have the turbulent and the laminar flow, depending on the water velocity, the pipe condition, and many other things. These are the two types of flow. In case if you have turbulent flow, the velocity distribution looks like the blue line. The thing that you will notice here is the velocity increases rapidly once you move away from the wall. So at the wall, it equals to 0. Once you move a very small distance, like 5 or 4 millimeters, you will reach a very high speed. This speed is approximately 0.4. In this example, the mean velocity is equal to 0.5, as shown here. The mean velocity of these two flow conditions is equal to 0.5. So for the turbulent flow, just moving away from the wall, you have almost reached the uniform velocity. While for the laminar flow, you actually don't reach the uniform velocity at all. You start at 0, and the velocity increases gradually up to twice the uniform flow, because the uniform flow in this case was 0.5, and at the center line of this pipe, the velocity distribution reaches 1 meter per second. Then, of course, it goes back to the 0 on the other wall. So again, this is not something related to the experiment, but it's very important to understand, because when we tell you that the discharge Q equals A multiplied by V, you might think that the velocity is constant, because we only gave you one V, right? Actually, the V that we gave you in this case is called the V mean, the mean velocity. So we are basically approximating the two shapes, the parabolic shape and the other shape, to a rectangular shape, and we tell you that the rectangular shape or the mean velocity is equal to something. Any questions before getting back to the main concept behind the experiment? Yeah, sure.
So this is mean velocity or the average velocity. So for the turbulent flow and the laminar flow,
Yeah.
it's not the same. Like
The approximation procedure is not the same. Like, to approximate the laminar flow
and the turbulence.
isn't the same.
Is it like the profile?
Yeah,
The profile is different.
yeah,
So that means like in the turbulence is not the change is like goes suddenly.
yes,
It's not because the vertex or something.
yeah,
So the average velocity we get is like we are looking to go close to the uniform flow to be able to solve the equation. But in reality, this velocity goes through equation like parabola equation.
yeah,
But if we using this just here like for assumption to go close to the uniform, we're able to use this equation.
yep.
But if we don't need to find the equation.
No, you don't need to do that. Like, no, you don't need to do that. Like,
No.
we do that before giving you the velocity, but after getting the velocity, the mean velocity, you just can plug it into a continuity equation to get the discharge. We don't need to do any like calculations or equation manipulation to convert from the velocity of the parabolic shape to the mean velocity.
Okay. So the device gonna give us.
Actually, if you just like waited for a couple of minutes, the device actually do not measure or doesn't measure the velocity or the discharge. It actually measures the pressure. So I will answer your question in a couple of minutes. But this is a very good notice that are we going to use the discharge measurements to get the velocity or the discharge? Actually, we are not going to get the velocity or the discharge from the measurement device. We are going to get something else, which is the pressure, as I am going to explain right now. So for the first experiment, we have the Venturi Tube. It is a very simple device. This device looks like this. In this orientation, the flow comes from left to right. It enters this section before constricting or before having the contraction to a smaller section. Then it comes back to the large section. But actually what we are interested in specifically is section number 1, which is the large section, and section number 3, which is the small section. So we already know that continuity equation says Q equal AV. Of course, because we have a constant discharge going inside this Venturi tube, the Q that is passing in the first section should be the same as the Q that is passing from the second section, right? So, of course, we know that obviously from the figure, A1 is much larger than A2, right? So what about the velocity? Do you think the velocity at section 1 will section 3. So let's just consider section 1 and section 3. So what about the velocity at section 1 and section 3? What is the relation between V1 and V3? Any ideas? Exactly, because we reduce the area, the velocity should increase because we have the same discharge. So in this case, V3 definitely will be larger than V1. Again, the device does not measure the velocity nor the discharge directly. It measures the pressure. So what's the relation between the velocity and the pressure? In other words, what about the pressure at section 1 and the pressure at section 3? If you take a look at equation number 2, which is the energy equation, for the left term, which is the energy at section 1, we have 3 components for that. We have the pressure, we have the elevation, Z, and we have the velocity component. Of course, at the same section, you have the same energy. So in case that the velocity increases, if this term increases, this term should decrease, because the result at the end should be the same. Because of course the Z won't decrease. Z is the elevation of the pipe. Like by reducing the cross-sectional area, no one can say that the pipe will go down or up. It won't move. So we can say that pressure 1 is much larger than pressure 2, pressure at section 3, because the velocity at section 3 is larger than velocity at section 1. We can recap what we said by saying that the pressure has an inverse velocity with an inverse relation with the velocity. Understood? Yep. I'm sorry? Alpha 1. Actually, alpha is a parameter that deals with the condition of the flow. If it's turbulent, if it's laminar, it's not something that we are going to deal with anyway, but in case of ideal situations, we just take alpha equal 1. In some situations, alpha does not equal 1 because there are some kind of vortices, as you say. This means that the velocity component won't be used as a whole as the velocity head. So that's why we use this alpha. But for our experience or for our example, we are going to use alpha to equal 1. But it's something related to the condition of the flow, if this answers your question. Great, so now we know what is the Venturi tube, what is the concept behind it. What it basically does is to reduce the cross-sectional area, to increase the velocity, and to reduce the pressure. To simplify things, we can derive a more easy equation or an easier equation from equation 1 and equation 2. And to do that, or after doing that, you will have equation number 3. And what equation number 3 tells you is the relation between the parameters like A, P, gamma, and the Q. So let's take each parameter and explain it. Of course, the area, A1 is the area at first section. A3 is the area at section number 3. And because you already know the diameter at these two sections, you can easily calculate the area of the sections. What about G? Of course, it's the gravitational acceleration, 9.81 meter per second square. And what about gamma? Is the unit weight of the water, which is 9,810 Newton per meter cubed. So what about the other parameters? The P parameter. We have here P1 minus P3, which we might call delta P, or the differential pressure, the difference between the pressure at section 1 and section 3. And this is actually what you can measure using any of these devices. It only gives you the pressure difference. And to understand how we get the pressure difference, we will explain that in details later, but just to let you know how we are going to do that. For example, let's say that we are going to use the Venturi Tube. We will insert it in this position. We will open the pump to allow water to pass through the device. Then we will connect two hoses coming from the Venturi Tube to this point here and this point here. After doing that, you will see that there is a device. Measure the differential pressure. You will see the differential pressure in this screen in the units of millibar. So this is how we will get the pressure difference, P1 minus P3. Once you get P1 minus P3, you can just substitute in equation and you can get the discharge very easy. The Venturi Tube device is almost the same as the Venturi Tube, but the idea behind getting the pressure is a little bit different. How? If you remember, in the Venturi Tube, we reduce the cross section to increase the velocity and reduce the pressure. But here for the Venturi Tube, we have another way to get the pressure difference. For this orientation, we have the flow coming from the left to the right. And you will notice that there are two small tubes, very small tubes. The L-shaped tube and the straight tube. The straight tube measures the static difference, the component of P over gamma plus Z. If you remember experiment 2, I think Matt did that experiment with you. There are two types, or originally there are three types of pressure. We have the total pressure, we have the static pressure, and we have the dynamic pressure. Do you remember that? So the first type, or the tube, the straight tube, only measures the static pressure, which we call B static, while the L-shaped tube measures the total pressure. And the total pressure, as per this equation, equals to the static pressure plus the dynamic pressure. If you remember, the dynamic pressure comes from the velocity of the flowing water. So once you have the total pressure that comes from the L-shaped tube and the static pressure from the straight tube, you can substitute in this equation to get the discharge. So what we are going to get from the Venturi Tube is the difference between the B total and the B static. Just add this to the equation, divide that by the density of the water. This variable indicates the density, rho, which is 1,000 kilogram per meter cubed. And here, this is the sectional area of the Venturi Tube. And how you can calculate the area, you will see that it already mentioned here that the diameter of the pipe of the Venturi tube assembly is 17 millimeter. Great. So, do you have any questions about how we can measure the flow rate from the Venturi tube? I mean by questions about the concept itself and about the experiment. So, any questions?
So in this case, we don't have change in the diameter. It's the same.
The diameter is the same. The only difference is that you are getting two different types of pressures. Yep. There is no change in area.
And the other equation,
It's the same, but in this case, it converts the B total minus B static by the pressure head, which is delta B gamma over M, because if you remember, there are two types of pressure. We have the pressure with the pressure units and the pressure head. And the pressure head, which is H pressure, can be calculated by using the pressure over gamma, the water. This term here. Can you see B1 over gamma? This is called the pressure head. So what it did is that it converted the pressure to the pressure head, but because we're already getting the pressure directly from the device, there is no need to convert that to pressure head. So there is no need to use this equation. It's the same equation, but there is no need to do this conversion. What question? Okay. The third device is the flow nozzle meter. And in flow nozzle meter, actually, we are reducing or we are changing the cross-sectional area. Why? Because here we have the orifice meter, or in our case, it is the nozzle meter. The flow comes from this section, and it passes through an area with full diameter. This is D1. This is the diameter of the first section. So just to not confuse you, let's consider that this is section 1 and this is section 2. So at section 1, the diameter is the whole diameter of the pipe. In this case, we have the diameter as 28.5. This is the diameter of the pipe. What about the other section? If you look closely to this plate here, it is magnified in this section, and you will see that we have reduced the diameter from 28.5 to only 14 millimeter. What does that mean? This means that in the first section, the water will be able to move and to fill this area, while for the second section, it can only fill this area only. What does that mean? This means that we have a change in area, so we have a change in velocity, and we have a change in pressure. And that's why you will see two pressure gauges, two pressure taps. The first one is at section 1, the second one is at section 2, and these two pressure taps will give you the pressure difference. Once you get the pressure difference from the flow nozzle meter, you will substitute with it in equation number 6, and again this is the density of the water, which is 1000 kilogram per cubic meter. So the whole idea behind this experiment is to get the pressure difference between two sections and apply any of these equations to get the discharge. And if you didn't notice that, equation 3, equation 5, and equation 6, all these equations were derived from the continuity and the energy equation. So that's why at the beginning of this lab, I told you are going to use the energy equation to measure the flow rate, because this is the main concept, or this is the main principle behind the experiment. Questions? Everything is clear? Great. So I will improve my calculations from equation 3, 5, and 6 by considering something called the discharge coefficient. And why I need to improve my measurements? Because actually, while driving the previous equations 3, 5, and 6, I have neglected a very important term in the energy equation, which is the head losses. You should be familiar with the head losses term from the lecture, but in case if you don't, the head losses is simply something to consider the energy that is lost within the pipe. Of course, if we have a pipe and there is a water flowing from the inside this pipe, it will have some friction with the wall. This consumes some of the water energy, and this energy can't be converted to any kind of potential or kinetic energy. This energy is totally lost. I can't use it anymore. So while driving the previous equation, we have just neglected this energy loss, which is not actually true. This is a wrong assumption, but just for simplification, I did it to be able to drive this equation. So to account for the head losses, I will have to consider the discharge coefficient. So basically, the discharge coefficient is a way to consider the head losses that have been neglected while driving the discharge equations. So how can I consider the discharge coefficient? Basically, you will say that the actual discharge that is passing through the pipe equals the calculated discharge from equation 3, 5, or 6, whatever, multiplied by another parameter called C, the discharge coefficient. And in this lab, we will know how we can get the discharge coefficient from some measurements. So, of course, we are going to do that in details, but is there any question about why I am using this equation and why I have to correct the calculated discharges to get the actual discharge? Great. Yeah.
So we have the actual, which is the measure, right?
Sorry?
The actual chart, the Q, which is the measure, right? Q measure.
Is the Q measure? Yeah, the one that I can measure from the displacement meter.
Oh,
Yeah. This meter here, the one that I showed to you at the beginning of this lab. Not sure why it's not opening. This one here is the displacement meter, which I can get the measured discharge. Anything else is calculated because you already will use your calculator to multiply the area by the square root of something. That's why it's called calculated discharge. But the measured discharge, or the actual discharge that I know that is actually passing through the system, can be measured from this equipment. And I'm going to show you how to do that in a while. So let's take a look on the procedures of the experiment. Again, we have 3 experiments, one for each device. The procedures are the same. There is no difference between them. I will start by install the device, the Venturi Tube, Venturi Tube, or the nozzle meter. Then I will switch on the pump so I can allow water to pass through the system. I will record the flow rate from the displacement flow meter, and this will be my measured discharge this will be, or this will represent the actual flow rate. And of course, I will have to get the pressure difference or the pressure differential from the pressure meter. Once I do that, I have finished the experiment, but we are going to do that 3 times. We are going for each experiment, we are going to make 3 trials. Each trial will be for a different flow rate. The first trial will be at flow rate 1.2, the second at 1, the third at 0.8 meter cube per hour. So someone might ask how I can control how can I control the flow rate? You will see that there is something called the control valve, this red circle here. This red circle can or allows you to control the flow. If it is fully open, it will allow more water to come to the system. This means that the flow rate is very high, and once you start to close the control valve, you will reduce the flow rate. So this is how you will determine the amount of flow that is passing into your system. So the same thing applies to the other experiments, so we won't repeat this. And let's go very quick to take a look on the worksheet. Again, I have updated the worksheet, so please try to download the most recent version on Blackboard and use this to submit it as your lab report. Okay, so for the first experiment, for the Venturi Tube, as you can see, the diameter of the Venturi section 1 and 3 is already given, so you can easily calculate the area from knowing this diameter, and of course it's a circular tube. The only thing that I want to remind you is the diameter is in millimeter, of course. This is a very small tube, and the area here is in meter square. So don't forget to convert from millimeter to meter. Don't forget to do this conversion. Okay, what about the next table? As you can see, for the first trial, the discharge equals 1.2. It asks you to get or to write down the pressure difference, delta P, with the units of Pascal. So if we take a look at the pressure meter that we have here, it gives the differential pressure in millimeter, not in Pascal. So you will have to take that into consideration. You will have to convert from millibar to Pascal. So to do that, let's say that we want to convert from millibar that we get from the pressure meter to Pascal. To do that, you will have to multiply by 100. So don't forget to do that. So whatever the measurement, you should multiply this by 100. Great. So for the calculated flow, of course, very easy. For the Venturi tube, you will use equation number 3. That is shown in your lab manual. Again, there is something that you should be very careful here. There is something tricky. If you did unit analysis for dimension analysis for equation number 3, you will see that the result, or I can say the values that this equation produces, is in meter cubed per second. Again, if you did a dimension analysis for every parameter in this equation, you will see that the results will be in meter cubed per second. But in the lab manual or in the worksheet, it asks you to get the calculated flow in meter cubed per hour. So what you should do in this case, you should convert from meter cubed per second, which is the results of equation number 3, to meter cubed per hour. And to do that, you will have to multiply the results from equation number 3 by 3,600. This is the conversion from meter cubed per second to meter cubed per hour. Any questions? Great. So the same thing applies on the Venturi tube. You have the diameter given. You will calculate the area. The same thing, the same measured flow. You will get the delta B for each trial. Use equation number 5 to get the calculated flow. Again, you will multiply this by 3,600, and the same thing for the nozzle. What about the questions? Actually, this experiment has many concepts that might be new, and you should be very familiar with them, because of course you will need them in other courses maybe. It's not something related to fluid mechanics. So for the first question, we already did that. We already calculated the volumetric flow rates by using the equations 3, 4, 5, and 6. While for the second question, it asks you to plot the relationship between the calculated flow as a function of the measured pressure differential delta B on an XY scatter plot, and you will do that only for Venturi tube experiment. There is no need to do that for the 3 experiments. You only do that for 1 experiment. Then it asks you, after plotting the relationship, it asks you about the relation. How are they related? It also asks you about the kind of this relationship. So is it linear? Is it non-linear? If it's non-linear, what's the type of this relationship? So before doing this with you guys, do you have any idea about the answer of these 2 questions? The first one, how are they related? And to make it easier for you to answer, there are 2 kinds of relationships, of course. Or there are 2 main kinds of relationships. Might be like direct relation or inverse relation. And I mean by direct relation, when something increases, the other increases. And the inverse, when something increases, the other thing decreases. So what do you think the relation between delta B and the Q is? Is it direct or inverse relation? Just by looking at the equation, you can answer this question by looking at equation number 5. Is it direct or inverse relation?
So when we increase the Q, that means we increase
So where is the delta B? Yeah. You would like to answer that? Direct. Yeah, it's direct. Exactly. Why? Because actually delta B is in the numerator of this equation. This means that when the delta B increases, the Q will increase. There is no other way. So this is the first, or this is the answer of the first question, is that they are directly related. And even if you couldn't get that from the equation itself, you can easily get that after drawing the relation between Q and delta B. And again, it asks you to draw delta B on the x-axis. So after doing that, you will see that the points that you have is something like that. So it can't be indirect, it should be direct. So let's go to the second question. What kind of relationship is this? What kind of relationship is this? So what are the kinds of relationships that we have? Mainly we have linear and non-linear relationships. And I mean by linear is that the relationship or the ratio between the dependent and the independent variable is a certain constant. I can define the linear relationship by saying y equal m, which is the slope, multiplied by x plus something or maybe plus 0. This is the linear relationship. If I have this c to equal 0, I can say that y over x equal m, which is the slope, which is constant for these two variables. So what about our case here? Do we have a constant ratio between q and delta p? So I can see someone saying no, which is actually, it's not linear. Why? Because, as you can see here, there is a square root. And of course, this square root will ruin everything. You can't have a linear relationship by having a square root. So to let you understand what I mean by linear or non-linear and fixed ratio, again guys, this is something that you will really need in any other course. This is something not related to hydraulics or fluids at all, but let's say that we have two trials, just for the sake of the example. We have trial number 1 and we have trial number 2. For trial number 1, the delta P was equal to P1, a certain value, P1. And for the second trial, the delta P was 4 P1, 4 times the P1. Okay? And the Q for the first experiment was Q1, any value. What will be the Q for the second trial? 2Q1 or 4Q1 or 3Q1? Yeah, it's gonna be 2Q1. Why is that? Because we have the square root. Okay, what about if we have like another trial, and in this time, instead of having 4B1, we have 8B1. What will be the Q for this trial? It will be the square root of 8 of Q1, right? So that's why the relationship isn't linear. If you try to draw the relationship between delta P and P, it won't increase by the same ratio. It will increase by the square root of the ratio. That's why it won't be linear. And we call this relationship as a quadratic relationship. So if you did that, you will see that the relationship between Q and P will be something like that. It's not a line, it is like a part of a parabola. So we call this as a quadratic relationship. Great, so this is the way that you will have to solve the second question. Actually, I prefer to do that with you guys because this will be more beneficial. Any questions before I go to the third question? No questions? Okay, so the third question asks you to plot the calculated flow on the x-axis and the measured flow on the y-axis for the 3 experiments. So I should have 3 plots. Each one represents each experiment. After plotting the calculated and the measured flow, it asks you to use these plots to estimate the flow coefficient C. Of course, we will have 3 C's, 3 flow coefficients, 1 for each device. So anyone knows why I need to draw the relationship between the calculated flow and the measured flow to get the flow coefficient?
So you find the graph of the C, so
Yep,
this one considers the head load, and from here you gotta find out.
exactly. I am going to plot the relationship between the calculated flow and the measured flow because I would like to know how does this relationship can be presented, because I know that Q measured equals C multiplied by Q calculated. So if I know the relation between the Q measured and the Q calculated, I can easily get C, because C equals QM over Q calculated, right? Someone might ask why I need to plot, because there is an easier way to get the C. For example, if I have calculated the flow rate, let's say that it was equal to 2, and this one equals to 1.8, and this one equals to 1.4, just for example, I can easily calculate the C for each trial by dividing 1.2 over 2, 1 over 1.8, 0.8 by 0.4. Then I can get these three values, and I can get the average of these values, right? I can say that C, in this case for the better tube, equals the first plus the second plus the third value divided by 3, and this is the C, right? You can do that very easy. Why do I need to plot? Because actually taking the average isn't that accurate. It's better to plot the relationship between QM and Q calculated and do some kind of fitting to get an accurate value for the discharge coefficient C. Why this will be accurate? Because of course it won't be very obvious in our example, because we only have 3 measurements or 3 trials. But in this case, the Q calculated will be on the x-axis, Q measured will be on the y-axis. And just for the sake of example, let's say that we have like 10 trials, not only 3, okay? Let's say that we have 10 trials. So I will plot the 10 trials, this one, this one, this one, this one here, and this one. So these are the trials. Of course, we only have 3, but I just would like you to understand the concept. So if I am taking the average of these 10 trials, this means that I am giving the trials the same weight. I'm just summing the trials, dividing it by its number, and this is it. This is the actual result. But if you have the plot of the QM versus Q calculated, you can do something, we call this curve fitting. We try to find the best fit, the best line that can pass through most of these points. Of course, I can't find a single line that passes through all of it, or all of them, but I can actually draw a line that is approximately passes through all of them. And I mean by approximately something very detailed, but we are not going to explain that. I am just trying to reduce the error between this line and the actual measurements that I am having. Because this difference, this small distance, is the error between the measurements and the line, right? This is the difference. In case if you are interested with knowing more about this thing, you just search for RSS, residual sum of squares, and you will find the whole explanation for that. But for our situation or for our experiment, the only thing that you should understand is we are using this method because we want to get an accurate estimation for the flow coefficients. Clear? Great. So how can I get the slope, or how can I get the C from this figure? Actually, C will equal to the slope. So if I was able to get the slope of this line, C will equal to the slope that is equal to delta y by delta x. So just pick any 2 points on the line, get the slope of the line, and this is it. This is the discharge coefficient. So just to make sure that you understood the idea correctly, what will happen if someone draw the relationship not between Q calculated on the x-axis, and instead he or she calculated or draw the Q measured on the x-axis and the Q calculated on the y-axis? So what will be the result? What will be the difference between this solution and the previous one?
Is it negative?
No, it won't be negative. The slope will be the inverse slope, because you actually switched the 2 sides. So in this case, if you did the QM on the x-axis and the Q calculated on the y-axis, the slope will be Q calculated over Q measured, which is not equal to the C. It equals to 1 over C, right? This is the inverse of C. So just keep that in mind in case if you somehow switch it the axes, you will have to take the inverse of the slope. One more thing, in case if someone of you guys used Excel to do that, and actually I recommend you to do it using Excel, because actually Excel will give you the best fit. You won't have to do that visually. You won't have to select the line by your own. It will directly give you the line that is perfectly fit these data. But there's only one simple thing that you should be very careful with. Anyone use that, or anyone tried to? So do you remember anything related to y-intercept? It's in the options of curve fitting. So what I mean is, what if Excel said that there is a certain line? So let's do that in orange. There is a certain line that looks, let's do something like black. I will use black this time. So let's say that the line that was perfectly fit this data was like that. So can I use this line to present the equation that I have? Why? It's actually, no, I can't, but why? Yep.
What the line is supposed to mean is the difference between two of these and by having them in a position that means where two count is 0, there's something like 2.
Exactly. This is totally correct. So what your friend said is that if I use the black line, this means that for somehow I can get Q measured, at Q measured equals 0, I can get a certain value for Q calculated, or vice versa. So let's just remove this. So if I am using the black line, this means that for a certain point at Q measured equals 0, at Q calculated equals 0, there is a value for Q measured, which can't happen, because once I have flow inside the system, I will have a value for the Q measured and Q calculated. So if you can't understand that, or if this is very hard for you to understand, there is a simpler way to make it easier for you. Just go back to the equation that I am trying to represent. I am trying to represent this equation. Qm equals C multiplied by Q calculated. So the equation of the black line is y equal slope multiplied by x plus a certain y-intercept, yc. But actually in the original equation we don't have this y-intercept. So I am using a line with a different equation to represent my equation, which isn't the same. While for the line in yellow, in blue, the equation of this line is y equal slope multiplied by x. So I can use this one, but I can't use this one. That's why, in case if you are going to use Excel, make sure that you have checked the y-intercept equal to 0 mark, because if you didn't do that, it might give you a wrong equation. So that's it for the explanation part, and let's go to the experiment, or the experiment part, to get the measurements. And actually we have two approaches to do that. In this experiment you won't be involved at all in taking any measurements. You will only be seeing what I'm doing. So we have two options. The first one is dividing you into groups, just to let you come closer to the equipment. And the other approach, if you can all see the equipment very clearly from your seat, we can just do the experiment once. So I'm giving you the choice here, so you tell me which one would you prefer. Is there anyone who can see the equipment? All of you can see it? And if there's anything that I want you to see it very clearly, I will try to use my camera and you will be able to see that in front of you, so this won't be an issue. Great, so let's open the worksheet to know what are the measurements that we will need to get. So for the first experiment, for the Venturi tube, so I will use my camera so you can see the Venturi tube very clearly. Here is the Venturi tube. It's a very simple equipment that has two inlets, inlet and outlet. I think it's better to see on the screen, it would be here. As you can see, the first section here, this is the large section. As you can see, there is a contraction in the middle. This bolt here is the bolt that I'm going to measure the pressure from. And this is the second bolt, or at least we can say the third bolt. You shouldn't be worried about the other bolts. What I am doing right now is connecting them together because they are leaking. So instead of getting like water spurts, I'm just connecting them together. Okay, so let's install let's attach the Venturi